In the Module 3 assignment, you're going to be using Google Earth to help visualize and better understand plate tectonics, to see how plates move, which directions they move, where the major plate boundaries are, etc. Google Earth is a really phenomenal and free tool for visualizing the Earth in all sorts of different ways. If you don't have access already, you can get free access to Google Earth by going to google.com/earth. There are a couple different ways of using Google Earth. If you're using the Chrome browser, you can launch Google Earth directly in the browser, nothing to download. You just click the blue button and Google Earth starts running right in the Chrome browser. However, the instructions for this assignment, as we've written them, assume you have the version downloaded to your computer. So if you don't have that already, I suggest you go here, click on Earth Versions, and it takes you to this screen. And then click here, and it provides the download to Google Earth Pro, which you then need to install. Once you install Google Earth Pro and have it up and running, here's the opening screen. At least on a Mac, and on a PC it would look quite similar. In the center here is, of course, the Earth. There are a couple of ways to navigate this Google Earth Pro. You can use the mouse and you can grab the Earth and move it left, right, up, down to rotate the Earth. You can also use the button or the little rolling ball in the middle of the mouse to zoom in and out. You can also use the controls here. These buttons on the bottom zoom in and out. These on top control the orientation of north. You can turn the Earth sideways or upside down or anything in between. And these in the middle control the orientation in terms of the tilt. Currently we're looking straight down on the Earth, but you can use those to control the angle at which you're viewing the planet. On the left-hand side are some important controls too, and the bottom one is called Layers, which is what it sounds like. You can show all sorts of things in Google Earth, a lot of things you'd expect like borders, labels of cities, rivers, etc. But there's a whole lot more here you can experiment with too. The middle box is things you'll download, and if you choose to save to Google Earth, I'll refer to them as layers. They're layers of things you can visualize that you can think of as being pasted on the outside of the globe. In the upper left box here is a search box, just what it sounds like. You can put in cities, your address, anything you can think of, click search, and if Google Earth knows about it, it will take you there and zoom in with incredible detail. So for this assignment, what you need to do is go back to D2L, and on the assignment page there's a link to download a file called Plate Boundaries. And once you download that file, on some computers Google Earth will open it automatically. On some, though, you have to go to Google Earth and sort of tell it where the file is. Go to File in Google Earth, click Open, and then navigate to wherever your downloads go, probably to the folder called Downloads. Open that file, and this is what you should see. We've basically taken the globe and overlaid on it the major plate boundaries, and here's the key. Red represent divergent plate boundaries, blue transform, yellow convergent, and white undefined. So the first set of questions is about the plate boundary in the western U.S. What we have here is this is the North American plate. On the bottom here is the Pacific plate. We also have this small piece called the Juan de Fuca plate here. So you're going to be looking at, in the beginning, the motion of the North American plate and the Pacific plate along this blue plate boundary here. You're also going to ask to zoom in on the Los Angeles and San Francisco area, which is approximately there. And that zoom in looks like this. And you'll be asked to think about the motion of cities Los Angeles, Riverside, and San Francisco, and how they're moving relative to one another given the plate boundary and the type of plate motion that occurs there. You'll be asked to then move up to the Pacific Northwest along the Cascadia subduction zone, where we have this small plate, the Juan de Fuca plate here, which is moving away from the Pacific plate, which is this one out here, and moving towards North American plate and moving underneath North America along this trench here, along this convergent plate boundary. You're going to be asked some questions about plate motion and the future of plate motion here, and how the motion of the Juan de Fuca relates to the Cascade volcano chain, which are all these little white dots here. Here's Mount Rainier, here's Mount St. Helens, Mount Adams, Mount Hood, the Three Sisters, Mount Shasta. There's a number of volcanoes along this line here. These are the Cascade volcanoes. and you're going to be asked to think a little bit about how and why those volcanoes are created and how they're related to motion of the Juan de Fuca plate. I'll give you one hint. A subducting plate, a plate moving underneath another one, the plate going down doesn't melt. There's some other process related to melting and creating of a chain of volcanoes that's explained in the textbook, but it's definitely not the downgoing plate. That one doesn't melt. Next part of the assignment is to look around the world at divergent plate boundaries and think a little bit about where they tend to occur. You're also going to be asked to look for a specific type of divergent plate boundary, one that's in a shallow ocean, and talk a little bit about how that plate boundary works. You're also going to be asked a question about the nature of divergent plate boundaries like this one, and why they have so many transform faults built into them. So here we have a plate which is moving, one is moving to the north, or up in this picture, and one is moving down in this view. And so the red lines here represent divergence, where the plate is moving up, the top plate is moving up, and so it's moving away from the bottom plate, which is moving down. And in between these red lines, we have all of these blue transform faults. So the question is to think about, or research, or read about, why do transform plate boundaries and divergent plate boundaries very often occur together like this? Why aren't divergent plate boundaries straight lines with one plate moving in one direction and one in the other? Why are they more often stair-step like this? So you'll have to read a little bit in the textbook, or do a little research on your own, or just think about it for yourself. The last part of the assignment is to look at this image. This map shows the age of the ocean lithosphere, and here's the scale bar. Here's the legend. Red represents young lithosphere, and blue and purple represent relatively old. I've also provided a link to another Google Earth layer to display the same information. That looks like this. So we've wrapped around the whole planet that map, and again we're displaying the age of the ocean floor, the age of the lithosphere, where red represents very young, and blue and purple represent relatively old. So you're going to be asked a few questions about the relative ages of the lithosphere, where you find young, where you find old, and why there's such a disparity between the age of the ocean lithosphere and the age of continents, which in general are much, much, much older. Okay, when you're finished, please upload this assignment as one file, please. Either as a Microsoft Word document or as a PDF, either's fine. Please send them to the Assignment 3 Dropbox, and let me know if you have any questions. Good luck.